High voltage direct currents, a super smart grid. I would like to start with the why. We are all well aware of the negative effects that mining's Earth's natural resources has, and that there is a real need to reduce our environmental impact. But how can we achieve this? Removing the Earth's limited resources is simply not a sustainable option anymore. Limited, meaning they do not rejuvenate. This, coupled with the fact that the demand for energy is expanding exponentially, is why we must now look at renewable energy sources that make use of natural sunlight and wind generation. The problem, though, is that we cannot simply put a solar or wind farm in the middle of a major city, or even suburbia for that matter, which ultimately means that we must move these power generation sources into remote locations such as out to sea, deserts, or other uninhabitable locations. This brings us to the main source of the problem: transmitting the electricity that is generated from these remote locations. The existing system that moves power from point A to point B relies on the alternating currents, which is unfortunately not a feasible transportation option over large distances. This is due to the amount of heat or power that is released from the lines during transport. Did you know over 10% of the world's energy is lost due to inefficient AC transmission? So, what is HVDC? HVDC is the potential solution to our problem. High voltage direct currents work by streamlining the flow of electrons into a singular direction, thus reducing the amount of heat loss during transmission. How does it work? It connects remote power generation locations to where the power is actually required. It does this through the process of converting bidirectional alternating current into unidirectional direct currents. What does this mean? Well, with conventional AC transmission, energy loss occurs through the rapid movement of electrons close to the transmission line surface. This creates what is known as energy seepage. By converting the electrons into direct currents, they penetrate deeper into the transmission lines and only move in one direction, thus drastically reducing the amount of seepage. This transportation takes place in two separate stages through the use of converter stations. First, the power needs to be converted from AC currents into DC currents in preparation to be transported hundreds, if not thousands of kilometres to where it is needed. Then, once the power has reached its destination, the process needs to be reversed, transforming the DC currents back into AC currents so it can be used to power our cities and homes. Some of the facts. Did you know Earth uses nearly 20 trillion kilowatts of power a year? And if HVDC is 30 to 50% more efficient than current methods, wouldn't it have a huge impact if we could integrate the two systems? Yes, it would. Plus, it has been calculated that over various distances, the DC system can offer between 30 and 70% financial savings, dependent upon the voltage requirement. So what are the limitations? The biggest constraint to this sustainable solution is money. Not only money for much needed R&D, but who is going to pay for the expensive startup costs, even though the ongoing costs can be reduced. Secondly, the technology is still not up to the desired standard, and small flaws in the system are still in the process of being fixed. These flaws include power faults, radio noise, electrocorrosion, all which can and will be fixed as time goes on. The fact is, we need to do something to preserve what we have, and this may well be our best option to becoming a sustainable planet. Thanks for listening.